and it's a pleasure to talk to you. Nice to see some familiar faces as well. I want to tell you a little bit about what we do in Tyndall, how it relates to what you do in your daily life in trying to enthuse students about physics and other sciences, and also a little bit about the research that we're doing. So the talk is entitled Materials Modelling for Devices, but it's really bringing together the different fields that you need to study this area. So Tyndall is just down the road on your way into Cork. It's a national institute. It grew out of the National Microelectronics Research Institute, and we're celebrating our 30th birthday this year. It was re-established as Tyndall in 2004 on the initiative of the government, and it's to be a sort of a national focus for taking electronics, taking the industry in Ireland in that space and having new application areas for electronics. So really looking 5 or 10 years out, what are we going to need for electronics in Ireland at that time? And we're really trying to help the Irish economy. That's our focus. So we're named after John Tyndall, you might know about, leading Victorian scientist born in County Carlow. So they're a little bit miffed that we've taken on the name down here. But when they get their own national institute, we'll give the name back, I'm sure. And the interesting thing is that, of course, he was the successor to Faraday in the Royal Institution and leader of the Royal Institution in London, so spent all his professional life in Britain. But he was probably in his time better known than Faraday as a communicator of science and a real personality in society at the time. He did a big lecture tour in America and raised loads of money. It was front page news that Tyndall was speaking on the scientific matters of the day. So I think that's a good example to us. And he did lots of, he was a real natural philosopher. He looked at glaciers, he looked at pasteurization, waveguides, you can say that he sort of invented. And the greenhouse effect, he was the first to recognize that some very small percentages of certain gases in the atmosphere had a disproportionate effect on the heating of the atmosphere, which is essentially the greenhouse effect. So we're proud to have Tyndall as our name. And it does mean that we're not limited then in what we do exactly, because Tyndall did absolutely everything. So in figures then, there's about 450 people down in Tyndall, of whom over 100 are PhD students. We don't have undergraduates except for projects. We do postgraduate education, and that's probably one of the most important things we do, is educate the graduates that are going to go out into Irish industry and society. And we have a clean room, so there's a picture of the clean room. This is sort of the electronics background, and it's a small clean room by international standards, but it's very flexible, so we can run small runs and do things for industry or for universities in the kind of environment you'd have in a real electronics company. Our turnover is there. We have lots and lots of industry partners, and that's a crucial part of what we do. And of course, patents and publications. And this is a little sketch of how the place is organized. We have different technical research centers in photonics, in electronics, microsystems, and then theory, which is the part I'm in. And in all of these areas, we really try to start with the fundamentals and then link through to actual systems that are actually going to be out there in daily life. So atoms, building devices, and then making systems out of them. And those are basically just some pictures to show you. I won't go through all those different things. It would take a long time. If you have 400 researchers, you're going to have a lot of research going on. And so I would like to stress that what I tell you about today is a tiny segment of what we do in Tyndall. And you're welcome to come and see the place and talk to me outside at the stand. There's a lot going on, and all of it is very interesting. So I'm best qualified to tell you about a small area. And it's the area of materials modelling, but aimed at devices. And this is really an area where electronics meets physics meets chemistry. So that's sort of how I'm going to structure it for you. So we'll start with electronics. For electronics, we're going to look at the example of manufacturing transistors. So transistors are the part of an electronic device where the ones and zeros are processed. You either get ones and zeros on, off. So this is how the data is actually processed into logic. It's the logic part of a computer. And this was the first transistor. And it was about this size. And it was, really made out of stuff. It's great. So Bardeen, Britton and Shockley, 1947, and that's how it all started, and it really worked. Then a crucial thing was where Kilby came along and said, you can integrate all the different wires and everything onto a circuit, and that was the start of the integrated circuit. And in a way, that really moved things forward. So, that was 10 years later, but that's when we could say the electronics business really got started. So the first one of the first circuits then, I've put a length scale on this. So we've blown up a 1 centimeter square integrated circuit, and there were 200 transistors on that. And that would have been made by hand using a microscope or something. You can imagine the work needed to fit 200 transistors onto this tiny, tiny little square. Okay, but that was just the start. So very soon afterwards, they developed the fabrication techniques, and now you could get 80,000 transistors onto this centimetre squared. So really it's all about, the principle was there. Bardeen and Shockley and so on had established the principle. Now can you fabricate it? So it's all about, can you make these things smaller and smaller? And so on it went. That was 1969. This is a more recent picture, say from 2008, where there's 2 billion transistors on a slightly larger chip. So this is the typical chip. If you opened up your computer, you'd see inside, packaged with all those little golden wires coming out of. They're accessing 2 billion transistors. And now 5 years later, things have kept moving. We're on a curve like this, and we have that still says 2 billion, that says 2011, I guess we're on to 2013 now, so the number is constantly increasing. This is something called Moore's Law. Gordon Moore, who was one of the founders of Intel, observed this, that every 18 months or so, the number of transistors on a given surface area seems to double. We seem to get better and better at doing it. And the reason it happens is money. I mean, that's the only reason Moore's Law works. You can make more money out of a given piece of silicon if you can put more chips on, more transistors on it. But it has been a remarkably steady pattern. And this is what drives Intel forward year after year, and all the other chip companies, to try to keep on Moore's Law. They fabricate the existing structures better, and they bring in new technologies to fabricate even smaller things as well that they couldn't do before. So it is remarkable that it's still going. You know, this is a log scale on the top, just that you're understanding here. This is a massive, massive increase in computing power, which is still going. And obviously when you have an exponential growth like this, everyone asks, is it going to end? When are we going to hit the limit, the wall? When is scaling going to stop? And in a way, scaling has stopped, and you never even noticed. Scaling is over. Physical scaling stopped about soon before 2008 because they hit a fundamental limit, which was in this little transistor, you have a little insulating layer. So I'll show you a video of this, but the video goes a little fast at the end, so you gotta keep up. It's a video from Intel on how all this works when they were bringing out this new. So there's a silicon wafer, one of these wafers that goes into the fab, and we'll zoom in and zoom in and zoom in. But when you get into the transistor right at the bottom, there's a little thin insulating layer, and that became too thin because scaling had just got so small and everything has to scale together, and the insulating layer got too thin, and you know what happens when an insulator is too thin? The current jumps across, so we got leakage. There we are, we're right into the bottom, right? There's the transistor. These are actual microscope pictures. There's the layer we're looking for, and now it goes very fast, unfortunately. Yeah, that's the old situation with an SiO2 insulator, and they needed a thicker one, because only physically thicker could you stop that leakage happening. So SiO2, silicon dioxide, reached its fundamental limit. End of story. It was a bit of a crisis in the electronics industry because you can't change how SiO2 behaves. So what you can do is bring in a new material, and that's what was done. And there was a big research effort in bringing in a newer material with a higher dielectric constant than silicon dioxide, so it behaved electrically like silicon dioxide, even though it was thicker. So it's a case where you weren't hitting that limit. And so this is the high K dielectric. And bringing in new materials allows you to continue scaling. It gives you a few extra years, and you can keep going with all the other parts of scaling that you need. So this is what happens in the electronics industry. And it's now new materials are driving scaling. And on top of that, now new architectures. We're going away from planar electronics and moving to stacking things. And obviously, you can pack a lot more stuff into space if you stack them in 3 dimensions. It's getting much more complicated, much more like a biological system maybe, where you have very complicated 3-dimensional structures at the nanoscale. So it's a really interesting time to be involved in electronics. And what it means is if new materials are now driving electronics, it's not just about making things smaller and smaller, it's about chemistry. So chemistry now has a big role to play in electronics. So this new material really changed the way electronic engineers think, and they're now actually going and talking to chemists and material scientists, and they realize that's what's needed for the future. So if you want to actually lay down a new material, so you have to lay down this hafnium oxide. Silicon oxide was easy to make, you just oxidize the silicon. Hafnium oxide is not so easy, and you needed a very, very thin layer. So I'll show you a little video of how the thin layers are put down. And this is a video we made. That's fine. This is a technique called atomic layer deposition. And if we press play. So atomic layer deposition is the best way of making very, very thin films. It's a type of chemical vapor deposition, which just means you take a chemical and you put it in the vapor, and then it deposits onto a surface and it grows. So this is a picture maybe of an ALD reactor, an atomic layer deposition reactor. There's the chamber. It's kept at low pressure. You put in your object. Now, for the silicon industry, it's a wafer, of course, but it doesn't actually matter. You can coat anything. And what I want to illustrate here is how ALD can coat any shape. So this is a very difficult thing to coat. How could you coat the inside of a fiber optic? And there's no other technique that could do this. So then you put your object in and you turn on the gases. Now there's two gases. We're going to make hafnium oxide. So we need a hafnium gas, which is hafnium tetrachloride, and an oxygen source, which is water. So that's not too hard. So there's the hafnium tetrachloride going in. It's a gas, chemical vapor deposition. And because it's a gas, it penetrates all parts of the object. And we'll zoom in on the surface, and when you get to the atomic scale, you see in comes the hafnium tetrachloride, and the surface is covered in OH groups, in hydroxyl groups, so they're little protons, and the protons go off with the chlorine to form HCl, and that reacts very nicely, very exothermic reaction, but then it stops. Once the chlorine is covered in the surface, there's no further reaction with hafnium tetrachloride, and it's no exaggeration to say that the entire inside of that fiber optic cable is now covered with a single atomic monolayer of chlorine atoms. Anyway, then you turn off the hafnium tetrachloride and let in the water. The water comes in, and the only place it sees chlorine atoms is on the surface, where we put them. And it reacts really violently and produces HCl, and then it stops. It's a self-terminating surface reaction. So this is really neat. By turning the valves on, off, and never letting the gases meet together in the gas phase, only letting them meet on the surface, we can grow it up layer by layer, atomic layer by atomic layer, as many layers as we want, just by switching the valves on and off. And this actually works. It's not just cartoons on a nice movie. This is how Intel make the hafnium oxide layers in computers. And since 2008, any decent-sized computer you've bought has these layers in it. So ALD is working. ALD works in the fab. That's the other thing. If you hear a lot about nanotechnology. This is nanotechnology that works in manufacturing, not just in the lab. So ALD is a useful and interesting area to work in, and in Tyndall we're doing a lot of work in it, because now they're looking at putting those materials into other areas of electronics. This is a reactor, the type of reactor you might have in an actual fab. So it's quite a big thing, it takes up like a whole room. And this was donated to us by one of the companies who make this equipment, called Applied Materials. So they supply the equipment for the fabs like Intel. Intel is full of machines, and all those machines come from some companies, and Applied Materials is one of those companies. So Applied are working with us in Tyndall to try to develop the new processes. It's like this is a big oven that only bakes one sort of cake, and you need a new recipe for each new cake. And so we're working with them to try to develop those new recipes. They also have a researcher in residence in Tyndall, so he's an applied researcher, but he spends all his time there, and that's really the best way to find out what's going on and to talk with us and develop new things. So it's all, equipment is good, but people are even better. So my area then is modeling. That's the experimental side, and it's great that we have so many good experiments going on. I'm trying to model that process. So all those kind of fuzzy points in the animation where it wasn't clear how the reaction was taking place, that's what we want to actually sort out. And for that, we have to turn to physics and quantum mechanics, because we do atomic scale calculations, and we need to know how bonds are being made and broken. So another equation, okay, but this is the only equation in my talk. And this is the Schrödinger equation again, but now it's the time-independent Schrödinger equation, which is just a little bit simpler. But again, it has a Hamiltonian in it. The Hamiltonian describes your system. And in our case, the system is atoms. So atoms consist of electrons and nuclei. Molecules, likewise, consist of electrons and nuclei. So simply what we do in our simulations is we arrange the nuclei in space, and we add the electrons, and that then is the Hamiltonian. The Hamiltonian says where they are and how they interact with one another. And we know how they interact. They have the Coulomb attraction and repulsion of electrostatics. So that's in the Hamiltonian, and that's known. What isn't known is the wave function and the energy, and that's what you have to then solve for. As we heard earlier, you make an ansatz and you try to see does the wave function fit, and you improve it. And so we have computer codes to do that. You cannot exactly solve the Schrödinger equation for anything more than the hydrogen atom, so we're kind of stuck, because we want to look at rather bigger systems. But you can approximately solve it, and you can approximately solve it to any level of accuracy, really. So in a sense, we can solve it if you have enough computer time, and that's the problem then. So for big systems with lots of atoms, you need a big computer. So we have computers at Tyndall. Obviously, every researcher in our group works on a computer every day, has a small computer on their desk like you might have at home. But then we also have a cluster of lots of computers linked together. We have about 2,000 cores linked together. and everyone in the centre can use that. We have access to the Irish National Facility. I don't know if you've ever heard of it. We have a really good computer in Ireland in the Irish Centre of High-End Computing. That's where the weather forecast is worked out every day. They do these 6-hour runs in time for the weather forecast. So when you see those models on the evening news, it's using that computer as well. We're one of the biggest users of that computer outside of, well, Met Éireann have their bit, but I think we probably use just as much. And then if we need to, we have access to European centres as well, which are really big computers. So we have the computing, and so we can look at systems of reasonably large size. So here are some examples from my colleagues. These have nothing to do with that deposition process. We're looking at lots of different things in Tyndall. These are 2 energy examples, actually. The first one is for photocatalysis, which is titanium dioxide is a material that when you shine UV light on it, it becomes catalytically active. So for example, it's used for self-cleaning, killing bacteria and things like that. If you TiO2 paint, it'll kill bacteria on it. Or for self-cleaning windows have TiO2 on them too. But the problem is it's only UV light that works. And that's not so practical if you want to actually use the sun's energy. So my colleague Michael Nolan has been looking how you can change that to make it absorb visible light. And he's put these different atoms on the surface there. It's a gallium oxide cluster put on the surface of the TiO2. And that changes the band gap, which means it changes the wavelength of the light it absorbs. And now he's got that to absorb visible light. And so the visible light should come in from the sun, generate electron and hole pair, and they go on and do the catalysis, which if in the case of water would be generating hydrogen. And if you can generate hydrogen from sunlight, you're on the way to solving the world's energy problems. But it's a step in the right direction. So that's a prediction he's made, and he's working with collaborators in Japan who can now make those clusters on surfaces. So another application on the right-hand side is also solar cells. It's amorphous silicon, the yellow or the silicon atoms. And we're trying to see where are the electrons in amorphous silicon, because there's questions there about how hydrogen affects that. So these calculations let us find out where the electrons are and where the atoms are. That's all I'd like you to take away. Now in my case, I'm looking at these molecules and these surfaces and how the reactions take place. So again, I can make a model of the chemical. This is, for the example, of copper. So there's a copper molecule. And because I'm a chemist, I can say the name, copper bis dimethylaminopropoxide. So we can compute the molecule, we can compute a surface with copper atoms, and we can compute the 2 together. And what we do is we put that together. So we just do 3 calculations, and then we put the numbers together to get the adsorption energy. And so we've described how adsorption of this molecule takes place onto a real copper surface. And that's the first step, right? The molecules come in, start to react. Then we break the ligands off. I mean, there's many more steps now after this. And putting all those steps together, we can describe the growth process. So that's the example of copper. We're only at the start of the copper story. Industry is very interested in copper, because if you remember that video from Intel, there were all those copper lines. There's a lot more copper in the chip than hafnium oxide or silicon. So they're very interested in copper, but we haven't got there yet. Lots of problems. One area, of course, that does work is hafnium oxide. So a student called Mahdi Shirazi, just finishing up, developed this model of how hafnium oxide grows. And that was that high-K material that they use in the chips for the transistor stack. He's handing in his PhD next week, so we've a good picture now of how this works. He took all those reactions, he found 150 different growth reactions, and he put them together into what's called a kinetic Monte Carlo simulator. And basically you roll a dice and you see which reaction occurs, and you roll a dice and see the next reaction that occurs. And you keep doing that a lot, and you use the computer, so it doesn't matter how often you do it. So you remember there were 2 pulses in ALD? So that's the red box and the blue box, is turning the pulses on and off. So the red box is the water, and the blue box is the hafnium-containing precursor, which was the green in the other movie. So I'm just, confusing you. And each time the pulse is on, reactions happen. About 175,000 reactions happen each time, but we're not showing all them. We're just showing a frame each time. And you can see gradually the film grows up. So the hafnium precursor comes in, it has its blue ligands attached, and then the water comes in and wipes those off and leaves hafnium oxide, and then the blue one comes in again, and it grows up. And this is the first simulation of its kind anywhere. So really no one else can do this kind of thing, and no one had this kind of atomic scale picture of how the growth occurs until now. So it's something we can use computers to do, put together lots and lots of events and see a complex behavior coming out. And you can compare this directly with the experiment. How fast does it grow? How much mass is deposited? What's the state of the hafnium atoms and so on. So it's really useful, and we're very excited with that. So I hope Maddie gets his PhD now, having done all that. So that's really all I wanted to tell you about. We need these different disciplines. They come together and we use them to try to solve problems for industry. In fact, our students come in and maybe they came from a physics background or a chemistry background. By the time they're finished in Tyndall, that's all gone. We don't even see that anymore. We're an interdisciplinary centre. We're just trying to solve problems for industry. In fact, this is what we want our students to think about and to go out thinking. We help industry in Ireland and around the world. We bring together academic researchers and the industrial partners. And the reason we do that is very clear. You know, Intel have a fab in Leixlip, and they're employing 3,000 people directly and 15,000 people indirectly. And they could leave. You know, there's other fabs in Israel, in Singapore, and so on, and Ireland has to compete all the time. And one of the things we compete on are the quality of our graduates and the quality of our school kids, the quality of our education system. So if we have an advantage in R&D in Leixlip, that's good for Ireland. So really, what we're trying to do is support the smart economy in Ireland. And that's what Tyndall is all about. So thank you very much for your attention.